visual representations of data, and they can be one-dimensional. A ruler or a thermometer are examples of a one-dimensional graph. They can be two-dimensional. We have an example here showing one direction or dimension is time, and the other direction or dimension is the percent change in the price of gasoline from the year before, thus creating a two-dimensional graph. Graphs can be three-dimensional, and we have an example in which our three variables are temperature, wind speed, and those two variables are used to compute the wind chill. Graphs could also be four-dimensional if you're able to add motion, and the motion has some meaning to the graph. That's a fourth-dimensional way to show some data and show some information. In our class, we'll be studying formulas, and most graphs can be modeled with formulas. Now, the more you know about different types of formulas, the more types of data that you'll be able to model. Here we have an example of some famous data. It's the CO2 levels at the Mauna Loa Observatory in Hawaii. And very interesting gentleman back in the 1950s started to record the CO2 levels, and it has been recorded ever since. You could see that as each year goes by, the CO2 levels fluctuate. But overall, since the 1950s, the amount of CO2 has certainly been rising. Hence, the up and down wave is waving around a parabola. So the function 4.5 times sine of 2 pi x plus 0.017 times the quantity x plus 5 squared plus 315 is actually a formula that models this data fairly closely. Now, we're studying college algebra, and so sine is an example of a trigonometric function in the next class that you will take, so we will not be studying sine waves. But the point of this slide is to illustrate that pretty much any data really can be modeled with a formula. You just have to know enough about various types of formulas and how to model. The points that make up a graph are the sets of values that make a formula true. Here we have an example two-dimensional formula, y equals x cubed divided by 2 plus 6. And the points that would make up its graph are such that if I plug a value in for the x and I follow the computation, the output that I get would be the y. So x would be one direction, y would be the other direction, and pairing up appropriate x's with their y's creates our graph. So for example, -2 for x gets paired with +2 for y, because when I plug -2 into the formula and finish the computation, I get +2. If I plug 10.5 in for x and follow the computation, I get 584.8125. So the point 10.5 for x, 584.8125 for y would be a point on this graph. If I plug in 0, I will get out 6. So 0, 6 would be a point on this graph, as well as 2, 10. If I plug +2 in and I cube it, I will get 8. 8 divided by 2 is 4. 4 plus 6 is 10. And notice, you can plug in nice clean numbers like 2, or you can plug in messy numbers like 4.83 and get out a messy number like 62.34. That doesn't change the fact that the point is on the graph. Here we have plotted the points that we calculated on the previous screen. X is being plotted horizontally and Y is being plotted vertically. So again, if I plug -2 into the formula, -2 cubed is -8, and -8 divided by 2 is -4, and -4 plus 6 is 2. So -2 is getting paired with 2. I am plotting -2 horizontally and +2 vertically. I know it doesn't really look like I've plotted 2, it almost looks like 0, but that's because my scale is going all the way from 0 to 600, and so positive 2 is going to look almost equal to 0 by the time you're trying to fit 600 onto your scale. If you plug 0 in for x, 0 cubed divided by 2 is 0, and 0 plus 6 is 6, so the point 0, 6 is on our graph, as well as 2 for x, 10 for y, 4.83 for x, and approximately 62.34 for y. And again, if I plug 10.5 in for the x and I cube that and divide by 2 and add 6, I get 584.8125. Now, in between all these values are other points. So if I pick a number between 2 and 4.83 and I plug it in, I'll get a y. That point will be somewhere in between the point 210 and the point 4.83, 62.34. The more and more points you plot, the more clear the graph is going to become, and then when you connect all of those dots, you will have the full graph. Here we have used the software Desmos, DESMOS.com, to graph this graph, and what it is doing, it's doing just what I was talking about. It has plugged in a whole bunch of values and calculated the y's very quickly and connected all of the dots and created a complete graph on the window -4 to 12. So notice we're only seeing the graph from x equals -4 to x equals 12 and y equals 0 to y equals 600. If I expanded my window, I'd see a little bit more on the left-hand side. But at some point, you have to kind of cut the window off. So I cut it off here, -4 to 12, 0 to 600 for the y's. Our previous example was an example of a function in which each x produces only one possible y output. But graphs can be created from formulas that aren't necessarily functions, but are perfectly good graphs. Here is an example following the formula x squared minus 2 times x times y plus y to the 4th divided by 4 equals 8. And any pair of x and y values that make that equation true will create a point that creates the graph. Here are several example points that do just that. If I plug these combination of values for x and y into the formula, I will get 8 as my calculation. Hence, those points are on the graph. For example, if I take -2.828 approximately, and I plug that in for x, and then I plug 0 in for y, and I follow the computation, I will end up getting 8. Again, I rounded the -2.828, so you probably won't get exactly 8, but imagine it's exactly 8. If I take +2 for x and 2.791 for y, and I follow the computation, 2 squared minus 2 times 2 for x times 2.791 for y plus 2.791 to the 4th divided by 4, I will get basically 8. So again, this is a set of example points that when you plug the x and the y into that formula that we showed on the previous screen, you get 8, and hence they satisfy the formula, and all of the points that satisfy that formula form the graph. If a point does not satisfy the formula, it is not on the graph. So if I take -2 for x and I do -2 squared, and I subtract 2 times x of -2 times y of 4, and I add 4 to the 4th divided by 4, I will not get 8. Hence, the point -2,4 is not on our graph. And we can see here that it doesn't fall on the purple squiggly oval shape that forms our graph. Circles are another example of a very important type of graph that does not fit the definition of a function, That is, almost all values of x that are on a circle have two possible outputs for y. So it does not fit that definition of a function where every x has only one y if it's fitting the definition of a function. But circles are certainly important, useful graphs, so we don't want to ignore them just because they don't fit the definition of a function. And some formulas that are not functions can easily be rewritten as functions that you put together to make the overall graph. So for example, this circle whose center is at 2, 5 and whose radius is 4, you could write the formula as x minus 2 squared plus y minus 5 squared equals 16. That is a formula that will create this circle centered at 2, 5 with radius 4. But I could rewrite that formula solved for y, and y would equal the square root of 16 minus x minus 2 squared plus 5. That would give the top of the circle. The bottom of the circle would be given by the function formula y equals negative 1 times the square root of 16 minus x minus 2 squared, then plus 5. And that would give the bottom of the circle. So this circle could be written as the formula x minus 2 squared plus y minus 5 squared equals 16, or it could be written as two different functions, one function for the top, one function for the bottom. Again, the top function would be y equals the square root of 16 minus x minus 2 squared plus 5. The bottom of the circle would be y equals negative square root of 16 minus x minus 2 squared plus 5. But once again, no matter what form of the formula you have, the combinations of x's and y's that make the equation true are the points that make up the circle. And I mean, in this case, it's a circle. So if I plug 2 in for x and 9 in for y, 2 minus 2 squared is 0, 9 minus 5 squared is 16. So 2, 9 is an example point on the circle. So is 4 for x and 1.536 for y. If I plug 4 in for x and 1.536 in for y, the equation is true whether I'm using one form or the other form. In our class of college algebra, we'll be studying some fairly common types of graphs, and we will study each of these types more thoroughly a little bit later in this unit and throughout the semester, but here we're just going to outline the names and a couple of facts about each of the types. So the first type we're going to mention are lines. Lines are a very common, very important type of function and graph. Lines are recognized in terms of their formula by the variables being raised only to the first power. So 3 times x minus 4 times y equals 7 is an example line. Y equals x divided by 2 minus 3 is an example line. X and y in both of those formulas are raised to the first power, or raised to the power of 1. Lines can be recognized by their graphs because they are straight. They are not curved. There's no curving at all in a line. And that is what really distinguishes a line from any other type of graph. Polynomials are functions or formulas in which the variables are raised only to whole number powers. So whole numbers means there is no fractional part, or the fractional part is 0. So 3.72, not a whole number. 3.00 is a whole number. So 0, 1, 2, 3, 4, 5 is an example list of whole numbers. So 0 and any positive integer is a whole number. So if you have a formula in which the variables that show up are only raised to whole number powers, you have a polynomial. And you can have any number of terms in your polynomial that can be raised to any whole numbers. We have 3 examples here. One example is a cubic, meaning the highest power is a 3. Another example is a quartic, meaning the highest power is a 4. Now, that quartic is not in standard form. It's in factored form. I can tell it's a quartic, though, because if I take those factors, x minus 3, and x plus 5 squared, and you add the powers on the factors, you'll get 4. So x is raised to the first power, x minus 3 is raised to the first power, x plus 5 is squared, so 1 plus 1 plus 2 is 4. And if I took the time to multiply out those factors and I put it in standard form, I would see that the highest power was a 4. And then the third example is a 5th degree polynomial. The highest power is a 5, and it is in standard form. So anyway, later in the semester, we will study polynomials some more. We'll point out some more features about their graphs. But for starters, we just want to make sure we know the definition. Parabolas, also called quadratics, are a type of polynomial that we will be studying quite a bit in our semester. They are polynomials where the highest power is 2. And you can write the equation in different forms. Any form can be rewritten in any of the other forms. So we have the standard form, x squared minus 6x plus 4 is our example, but it's standard form when you have the squared term first and then the term with x to the first power and then your constant. That's considered standard form. Then you have completed square or vertex form, and our example is y equals 2 times the quantity x minus 1 squared minus 5. That's called completed square form or vertex form. And the vertex is the point at which the curve turns. And so that's called vertex form because I can tell that this parabola has a vertex at x equals 1, y equals negative 5. And you also could have a parabola written in factored form. So our third example is in factored form, 1/2 times the factor x minus 8 times the factor x plus 12. But I can tell that it's a parabola because I have 2 factors, and if I multiplied them out, I would have x to the second power as the highest power. So I can see that I'm going to get a 2 as the highest power when I multiply those factors together. We are pointing out here that if you switch the vertical and horizontal variables, so I'm now putting the vertical variable in to the formula and computing the horizontal variable, when the highest power is 2, I still get the same basic shape of a parabola, it's just turned on its side. Rational functions are polynomials divided by polynomials. Our example here has a linear polynomial, 2x minus 4, being divided by a quadratic polynomial, 4x squared minus 12x plus 3. And rational functions often have graphs chopped up into pieces where the pieces are defined by the zeros of the denominator. So if I found the zeros of this denominator, I would kind of see that it's separating the graph into those 3 pieces. Again, we're going to study rational functions much more in our semester. We're just introducing the names of our types of functions. Now think carefully about exponential function. Exponential functions have that name because the input variable is in the exponent. So here we have an example where 1,000 is the coefficient. That coefficient is being multiplied by 2, and the 2 is being raised to a power or exponent of 0.25x. So my input variable is in the exponent. We are almost done with our basic list of functions, but before we do the last two, let us think about this idea of inverse functions. If I reverse input and output, I create an inverse function. If you swap x and y, you're creating an inverse function. All inverse functions, if you graph them, you will see that their graphs are reflections about the line y equals x. Here we have the example, y equals 1 minus 4x cubed. If I put 1 in for x, 1 minus 4 times 1 cubed is negative 3. Its inverse function will now have me plug in the negative 3 for the x. I will get out 1 for the y. So the inverse function is 1 minus x divided by 4 to the 1/3 exponent. You also could write that 1/3 power as a root, like a square root symbol with a little 3. That's another way to express this inverse function. So again, we'll study this topic some more. We're just introducing the definition right now. So the definition of inverse functions is when you swap the inputs and outputs. What was x is now y, what was y is now x. And if you graph any inverse functions, you will see that their graphs are symmetric or reflections of each other about the line y equals x. Our last few example functions are examples of inverse functions. For x squared, the inverse function is the square root of x, or x to the 1/2 power. They're both equivalent. You could write it either way. And the graph of a square root function is half of a parabola turned on its side. Again, if you're officially following the definition of a function, each x can have only one output. And so when you define the square root, you only take half of your parabola and you make the reflection about the line y equals x. So we have kind of a sideways parabola, but only half of a sideways parabola for the graph of the square root of x. Any power actually has an inverse, which is the reciprocal of the power. So x cubed, the cube root of x is the inverse function. You can also write the cube root of x as x to the 1/3 power. If I take x to the 4th, its inverse function will be the 4th root of x. You could also write that as x to the 1/4 power. If I have x to the 5th, the 5th root of x is the inverse function. I can also write that as x to the 1/5 power, etc. So any power function, the reciprocal of the power is its inverse. And the last function that we will define are the inverses of exponential functions. And the name given to the inverse of exponential functions is logarithmic function. So y equals 2 to the x is an exponential function. The variable is in an exponent. Its inverse is called log base 2. And notice its graph, by the definition of what inverse functions are, is the reflection of 2 to the x about the line y equals x. So again, notation has to be made up in order to represent these ideas. So, math is a language where you make up words and make up notation to represent your ideas. So the notation that was made up to mean the inverse of an exponential function is the name logarithm. And you denote what base you're working in, kind of similar to how you do with roots. A square root, a cube root, a 4th root. So if your base of your exponential function is 2, the log will be log base 2. If the base of your exponential function is 10, then your logarithm will be log base 10, and we'll use that notation. The main idea in this video was really about how sets of values that make an equation true make up the points of a graph. That was really the main idea. And then we pointed out that graphs really can be 2-dimensional or 3-dimensional or even 4-dimensional if you add motion to your graph. You can have graphs that fit the definition of a function in which each input has only one output, but functions are not the end-all be-all. There's plenty of important graphs that are not functions, and circles is one basic example of that. But all graphs are sets of points which satisfy a formula, and points that do not satisfy the formula will not be on the graph. And then we went through the names of the basic functions that we will study in this college algebra class, and we also went over the idea of what an inverse function is. So inverse functions swap the inputs and the outputs. What you were plugging in, you are now getting out as an output. All right, well, onward to the rest of our semester.